All right, so now we have our training set and our test set that we split our data into. We built our machine learning model on that training set. We built our decision trees, and then now we need to kind of evaluate how well that model is doing, right? We hold out that test set, and we need to kind of see how well the predictions do on that test set. So in this video, we're going to be going over all the different metrics that we could use to evaluate these models. Okay, so suppose we have this machine learning model, we fit it on the training set, we need to evaluate on the test set. How would we do this? So let's kind of back up a little bit and think about how we should view these predictions on the test set. All right, so suppose this was our data set for the test set. Right, so these are just the 7 data points that were held out. Generally, you'll have more, but this is just kind of an example. Basically, we have the horsepower miles per gallon for each of these data points that were randomly chosen, and the actual outcome, whether it was a success or a failure. Right? And so what we do is we built our machine learning model, we built our decision trees, and we have that kind of tree diagram to figure out what the prediction is for each of these data points. And so, if we follow that along, we'll find that, these are the predictions. Success, failure, 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 success, success. All right. So we have what actually happened. We have that outcome. And we have the prediction of what would have happened. And so let's actually kind of put this into a table. Now, this is what's called a confusion matrix. And so basically what this means is that this is just kind of a matrix that shows how confused the computer or the machine learning model is at predicting successes and failures. Right? So basically we have predicted success and failure and then actual success and failure. And so based on this, we can look at, for example, how many predicted successes were actual successes, or how many. Okay, so we're going to be looking at this table a lot. This kind of succinctly describes the information that we need from our predictions and from what actually happened. Right, so let's look at our first measure, and that's accuracy. Right, so this might make sense to you, just kind of all the predictions that happen to come true. Right, so for example, on our table, we had 1 predicted success that was actually a success, 3 predicted failures that were actually failures, and then everything else was not actually true, right? So in this case, you might have an accuracy of 4/7, right? So we have 1 plus 3 are actual, accurate predictions, and then the denominator is just all of the predictions that we made. One thing to note, though, is that accuracy is actually not a very good measure. You might think that that's kind of a basic measure that you might use, kind of accuracy just makes sense, but a lot of times accuracy is actually very bad. And so to give an example, let's consider this. Suppose you want to detect credit card fraud to decide which accounts to shut down. It is estimated that 99.9% of accounts are not fraudulent, right? So vast majority of accounts are legit, but there's some very rare cases of fraud happening. So we want to be able to kind of detect those cases of fraud. Now, what happens if you, predict every single account to be not fraudulent? Well, since 99% of them aren't fraudulent, you get 99.9% accuracy. But this isn't helpful at all, right? We're just predicting everything to be not fraudulent. We have a really good accuracy, but this doesn't give you anything, right? You're not predicting anything to be fraudulent, which is really the point of the whole process anyway. Right? We aren't detecting any credit card fraud. Right? So basically, in these cases, we have such a large imbalance between your true and false cases, your positive and negative cases. Something like accuracy isn't going to be very good. So what else should you use? Well, this is one possibility. So precision is given by the true positives over all positive predictions. In other words, basically, precision is how correct your positive predictions are, right? So basically, in our example, we have predicted success. We predicted 3 total successes. And so we saw that one of these three successes was actually a success, right? So basically, we have that kind of row predicted success, one for the actual successes, and then 1 plus 2 for the total number of times we predicted success. Right? And so precision is just a measure of, I predicted success this many times. How many of those were actually right? And so, this does a better job of kind of getting at what you want. And then also there's recall. Right? So recall is given by true positives over all actual positives. And basically, in the world out there, there's just the actual number of positives there are, and recall is just how many of those you were able to recover. Basically, how effective were you at getting all of those positives? And so going back to this table, what we have is on that column of successes, all the successes in that test set, there were 2. One of those we were able to get back. We were able to predict one of those successes. And so that gives us a 0.5 recall. Right, so basically, these are just kind of 2 other measures that you can use that might show how well your model is doing. Right? But, there's no standard, there's no number or cutoff that determines what's a good precision or recall. So let's take an example of the same thing that we looked at before, the credit card fraud. So if we think about this case, if we chose fraudulent accounts at random, let's say we just chose 100 random accounts or 1,000 different random accounts, just kind of randomly chose fraudulent accounts. We'd have a precision of about 0.1%. And this is because there's 99.9% not fraudulent accounts, right? Basically, we are just randomly choosing these accounts, and we're just going to randomly say these are the fraudulent ones. And so because there's so few fraudulent accounts, that's not going to be very good. So a model with 10% precision is actually really good. Basically, being able to say that out of all the positive predictions that I've made, 10% of those are actually fraudulent. It is a huge improvement over 0.1% of those, because that's 100 times lift over random chance. Right. So let's look at the other end. What if what would a model with 10% recall be considered good in this case? Well, if we chose 1% of all accounts randomly to flag as fraudulent, then a recall would be 1%. Right? Basically, just kind of if you choose all of them, 100% of them to flag as fraudulent, then a recall is 100%. Just kind of the percentage of all accounts that you randomly choose is going to be your recall. If our model flags 1% of all accounts as fraudulent and our recall is 10%, then it's giving us a 10% lift, or 10 times lift over random chance. So, just this improvement that we get with our model is what we're interested in. Just because we have 10% recall, which might seem low, doesn't mean that's bad. It's just looking at what makes sense and just looking at how much of an improvement we get over random chance or other models, just kind of compared to all the different models that you might have run. Right? And so what you should use really depends on what your question is, right? So you have precision, you have recall, you have accuracy too, which generally you don't want to use, but what you should focus on really depends. So let's go back to our initial question, right? Suppose a car company wants to decide which cars to buy ad time for. Basically, which car should the company buy ad time for? Well, in this case, we might actually want to use precision because the Super Bowl ads are expensive. And so, when you identify something as positive, when you identify something as going to be successful, you really want it to be successful, because if it's not, you're going to lose a lot of money. And so, it's less important that you get that recall. Out of all the possible cars that could have been successful, you don't necessarily need all of them to be successful. What's more important is that you don't want to waste money on unsuccessful campaigns. And so That's why it might make sense to use precision. In other cases, recall might make more sense. For example, for something like a very deadly disease, in those cases, it might make sense to prioritize recall because you really want to save people's lives. And a lot of money spent might not necessarily matter as much as saving as many lives as you can.